Yeah.
Is it possible to set it up so that we can have our thermometer sticking out so we can use the fractionating tube rather than the drying tube so we get better fractions? So it just, like the vapors separate better, or is it not possible to do that?
Not really possible. The hood is only this high. We also don't have enough actual fractionating columns to use. So, fortunately not. Question?
Just a review from the Acidbase stuff. When you're seeing molecule of Acidbase, and you have electronegativity versus size. Do you always use size when you have both options available?
When do you use size? Straight up and down the group. I need a more specific question.
So when you have like the warm up, you have chlorine and chloride and to an alcohol. Which one do you choose? You choose based off of electronegativity or size?
I didn't hear you. You said warm up page?
Yeah.
Warm up page, which page?
Acidbase warm up.
Okay. Which one?
The second one.
Second one? Okay. Which alcohol is more acidic? Which one?
First one.
No. Not with acidic.
Would be second one would be
Okay. Why did you choose the one with the chlorine? I need you to yell.
I thought it was
Everybody needs to hear, guys. I don't want to keep repeating this. If you need to stand up, let's make sure everybody hears.
I
Okay.
thought it was bigger due to size.
The charge is not on the chlorine, though. Is it? Then it doesn't matter. Charge only matters when we're talking about a charged atom. The charged atom that's bigger is more stable. The charge is not on the chlorine in this example. The answer here is inductive effect. And which is a stronger inductive withdrawing group?
Chlorine with more
F. F. Or electronegative. Okay, guys. Physical properties, that was my video. Yeah. Acid base. But didn't I send out the answer key to the warm-up page? Is that right?
Yeah.
Okay. Was it not explained in the answer key?
No, I haven't checked it. I was just
Haven't checked. Okay. I would check the answer key. Predicting acid-base equilibrium. Down here on the bottom, do we have a answer here? Somebody have answer here? Somebody have answer here? Am I going to be able to get back there quick? Can you meet me halfway? Your answer seems reasonable. Your mechanism is backwards, completely backwards. I wonder if it's because you're saying a base accepts a proton. Okay. I would say base takes a proton. That will help you with your arrow movement. If that was graded, if that was a mechanism question being graded, you would get 0 points. Question? Oh, you have it. Mechanism is reasonable. You need to draw out a bond, though. Okay, you have no bond between the oxygen and the OH. There's no bond there, and so that arrow is kind of meaningless because you're not really showing anything. Draw out a bond, then your arrow can be more meaningful. Okay? And we said that. I've said it a couple of times here. I think it's, well, it may not be written. It'll be written in the next mechanism handout. Okay? All right, where's the most acidic H on the board? Got only CHs. I got an OH here. Where would you rather make a minus? Yes. Okay, let's draw out the H. We got to have a bond if we're going to do a mechanism. Okay? Structures aren't always going to be drawn out, ready to go with mechanisms. Where's the most basic atom on the board?
Nitrogen.
Over here. These electrons do what? They go and bond to the H. Yeah? Your arrow is backwards?
Yes, sir.
Question?
So, looking at the pKa's, it looks like the one on the left.
Let's first show the result.
Okay.
Here, before we start judging which side. Maybe that side is not favored, but an acid-base reaction, the only theoretical reaction is this one. Strongest acid reacting to the strongest base. These electrons here move on to oxygen. Since I have a bond there, I can show them the bond being broken, moving on to oxygen, yeah? What does that arrow movement give? Oxygen now bonded to H, right? That's what that arrow means. That's a positive charge. So there's no longer a standard nitrogen. Make sure you draw your charge closer to the atom. Plus what? Plus the O minus. Why is it O minus? Well, there's two lone pairs here, right? Standard oxygen. The bonding pair moves on to the oxygen as the third lone pair. That's why there's now three. And that oxygen is a minus, yeah? There you go. That's a result, theoretical result of an acid-base reaction. Which side is favored? What's the acid over here? Thing with the H. 10. What's the acid over here? The thing with the H. What's its pKa? 5. Which side's favored? 10 or 5? 10. This side's favored. By how much? Favored by 10 to the 5. 100,000. At equilibrium, you got 100,000 of these type molecules and only one of these. That is 100,000 of these and only one is protonated. Only one out of 100,000. That's very minimal, right? So, question, is this called pyridine? It's analogous to benzene, but with a nitrogen. It's a weak base. Lone pairs in what type of orbital? Yeah, you got that, yeah? Is pyridine strong enough to deprotonate? This is called phenol. It's a phenol functional group, but it's also just phenol. Is pyridine strong enough to deprotonate phenol? No, it's a lousy base in this case. It's only going to deprotonate 1 out of 100,000. That's kind of, you know, you're trying to get 100,000 people to do something, only one of them did it. Do you think you're successful? No, pyridine is not a strong enough base to do this. Theoretically, that's what we could get. How do you do on that, guys? Pretty straightforward? Next one. Where's the most acidic H on the board?
The nitrogen on the left side.
I got CH, NH, OH. This is a carboxylic acid. There's your H. Where's the most basic atom on the board? Over here. Okay, this may happen internally. Your mechanism may happen internally. It could. Or we could just have another molecule. This is an alpha amino acid with different R groups, yeah? Let's draw out the bond here. These electrons take the H, these move on to oxygen. And the result is going to be minus there, and the nitrogen is now what? We got 3 H's. I'll draw them out. You can draw it condensed, perhaps, if you want, but if I'm clear, I would draw things out. Positive. That's going to be minus, and that's an R group. I'm only showing one molecule over here. How did the oxygen of the molecule become minus? Well, you look right here, right? This end is going to become minus. The nitrogen end is going to pick up a proton, and it will become positive. And that's just showing one molecule where both ends have done the business. Which side is favored? What's the acid over here? Right there, 5. What's the acid over here? The thing that has the H. That. What's its pKa? 10. Which side's favored? 5 or 10?
10.
10 is favored. This is actually favored. By how much? 10 to the 5 again, right? But this side, the products are favored by 10 to the 5. So that means every 100,000 of these you have, all but one is converted to this. That's pretty darn good. If you can get 999,000 out of 100,000, that's a pretty good job. No equilibrium is ever going to be 100% complete. So, this is an alpha amino acid. You see these in biology, you have different R groups, neutral side chains, basic side chains, acidic side chains. Yes. But this is the business end. That's alpha, the first carbon away from your carboxyl. Alpha, beta, gamma. But the amino is on the alpha. Alpha amino acid. How do these exist primarily? Do they exist like this? Or do they primarily exist like this? Primarily exists like this. You can't separate the acid from the base. It's in the same molecule. What's the name for a molecule that has 2 charges yet it's net neutral? Starts with a Z. Yes, where have you heard that before? You read textbooks? Okay. Zwitzer ion. Okay, that sounds German to me. Zwitzer ion. Anybody know German? Net neutral but has 2 charges. Solubility. Do you think this is going to be soluble in water?
Yeah.
It primarily exists like this. It's basically ionic, isn't it? It is ionic. The predominant form is ionic. Amino acids tend to be quite soluble in water. But guess what? You're usually it'll be shown like that. That's how most textbooks will show it. We just have to know as chemists that it really exists like this because of the acid-base chemistry that is going on and that it will go on. Okay? But we're predicting acid and base. We're using pKa's to judge equilibrium. We're drawing structures correctly. We're using mechanism arrows correctly. Okay? Many facets to this. Okay. I'm going to move on. Free information in the back. Yeah? There's some loose ends here, but we need to move on. We'll tie things up when we can. Our first test is when? Is it Monday or Wednesday? Wednesday. 2 weeks from yesterday. 2 weeks from last lecture. Okay. We're off on Monday, is that right? Okay. Next Friday, I may do a review session before class, like at 7:30 or 7:15 even. If you're interested, let me know. Okay, we need to move on. Again, we'll try to pull together loose ends. We want to cover some new material today. DQ page, yeah? How are we doing on there? We got an acid base there. Anybody got this one answered? Several acid base questions. Anybody have a question about DQ page? Okay, we have a purple. And then the one you printed yourself, alkane, cycloalkane. Nomenclature. How are we doing on nomenclature? Any questions there? Question?
So will it always be considered the parent chain even though they
Yeah, typically the ring is going to be your pair, like propyl cyclohexane. The cyclohexane with a propyl group on it. What you want numbering, one butyl, two propyl cyclohexane. Okay, so the alkyl groups were sufficient on the cycloalkane. Other questions about nomenclature? Yes.
So if there is a compound with two rings, how do you identify the parent ring?
I don't know that we would be doing that.
Okay.
Nomenclature can grow to become very complex. I mean, we're here. You asked a question that took us here. All right. Here's a lot more. You can get a nomenclature book, IUPAC book. We're covering basically the first 3 pages over the course. Okay. Other questions about nomenclature? Okay, there's some important stuff here. Important stuff. I think I want to know. All right, I'm trying to see how we're going to go today. I reckon I'll just do here. I'm going to jump ahead a little bit. Previous stuff we'll pick up. But because we're going to be off on Monday, I want to kind of introduce some things so you can be looking at these things. Okay, I think I'll start here. Here we go. Let's go for it. Cycloalkanes, particularly since the question was mentioned right here. Yeah. These are hydrocarbons, alkanes, which implies saturated hydrocarbons. So these have a ring. Okay. The smallest ring you can have is a 3-member ring. It's called cyclopropane, cyclobutane, cyclohexane. Yeah? Hey, now my bonds don't always connect. Okay? So you try to do it. If I try to connect them, they're going to look not as good. Okay? Cyclohexane is actually a useful solvent in the lab. I think cyclopropane is actually a gas at room temperature, so you can't use that as a solvent. But hexane and cyclohexane are actually common solvents for that, because they have good boiling points of about 60 to 80 degrees. Okay, the things to know. These actually have what's called ring strain, angle strain. That's because for 9th grade geometry, what angle is that right there? That's 60 degrees, okay? But that's an sp3 carbon. By the way, what's the formula of cyclopropane? C3H. Okay. You can count them. There's 2 H's on each carbon. It's 6. How do you know it's C3H6? I know it because I see 1 DUS, and thus it ain't C3H8. It's 2 less of C3H6. But you see the 2 H's on each carbon? Yeah. Okay. That's a tetrahedral carbon. Bond angle is, in general, it should be 109.5. Okay? Let's pretend it's 109.5 here. But when this compound is made, Mother Nature or something, okay, heat or energy, forced it to go to 60. Okay? And it made a ring, but it's, okay? But that force led to strain. And that strain is higher in energy because here I am relaxing on a Sunday afternoon, 109.5, but someone came along and, now I can't relax. I'm sitting here like this. I'm higher in energy because of the strain. All right? This also has strain. 9th grade geometry tells us that should be 90, but it wants to be 109.5. All right? So these electrons, why 109.5 electrons are more spread out? When we push them together, the electrons start not liking each other as much. They're too close. These others have good bond angles. They're wider. They're more closer than 109.5. I can go ahead and say your 5 and 6 are your best size rings. Okay? The larger are possible. I'm going to show them. When you get larger, you actually open up too much, and you go the other way. It's not as bad as some of these. Of the smaller ones. In the end, 5 and 6 are your best size rings because they have the most appropriate bond angles for the around between the CCC. Okay. How do we know the energy? Well, it comes from looking at heats of formation. And if you look at the heat of formation, the H of F for cyclopropane, you see it, and butane, actually positive here. But the others are negative, particularly those two, negative. What does that tell us? Well, this is heats of formation. You see that in Gym Chem? Is a resounding no?
Yeah.
Okay. So you should know what heats of formation are and how to use them. What does it mean? What does it tell you when you see that these are positive? Now, these are experimental values. This can be determined in lab. Positive tells you what? Okay, what is endotherm? What reaction? Yes, to form these, to create those, it requires energy. Why does it require energy to make these? Because something has to force these electrons closer together. Okay? Make these from what?
Straight carbon chain.
No, an H of F is making a compound from what?
Elements.
Elements. And in this case, that would be what? Carbon plus what? H2 plus H, hydrogen is diatomic, to give cyclopropane. You can balance that. How many carbons do we need?
3.
How many H2s do we need?
6 total.
Yes. There you go. Now you have a balanced supply reaction. And the delta H of that is called the heat of formation because we made the compound from the elements. Okay? Now this is theoretical. That could be made many other ways. But this is based on coming from the elements, and then this can be calculated. Why are these negative? Why are the other two negative? That means when you make it, heat is released. Why would heat be released? Well, it's more stable, but why more stable? That's the old Bill Gates question. Okay. Why is Bill Gates rich? The answer should not be because he has a lot of money. That's not really the answer. That's just restating the question, right? Then I have to ask you, well, why does he have a lot of money? Okay, let's get to a deeper answer. Okay. Why is it negative? Well, here's the take home here. Cyclopropane has lots of covalent bonds compared to over here. And making all those covalent bonds is typically an exothermic process. That's why most are exothermic. But not in the case of these two. Because the overriding factor was the strain that had to be put in. The energy has to be put in, and we see that. We see the strain energy from the H and F numbers. Okay? Hopefully that makes sense, yeah? Questions? Using numbers there? Okay. Intro to disubstituted cyclohexanes. We're going to focus on cyclohexanes. And then we'll start doing conformations and models. Okay? 6-membered cyclohexane. Disubstituted. If there was only one methyl there, that would be methyl cyclohexane. You don't need a 1, do you? Because the methyl could be anywhere and it's the same thing. We put 2 up there. Now we have relative positioning. Because they could be next door to each other or away or further away. These 3 are different constitutional isomers, yeah? Yeah. Which definition is what? You got your definition? Good to go?
Same formula, but different.
Does this meet the definition of constitutional isomer? This is called the 1,2 isomer because if this is 1, the other one's at the 2 position. And I could have said 1, 2 the other way, same thing. If this is 1, the other one is at the 3. So it's a 1-3 relationship. And this would be 1,4. Okay? So different constitutional isomers. And the fact that this has different numbering tells you it's constitutional isomer. Because the other type of isomer is not going to have different numbering when we get to it. Okay. For example, we're already there. But only a little bit. We'll mostly cover this type of stuff during test 2. But here we will introduce it. Let's focus on the 1,2. You can actually have two different isomers here, or configurations. That is, the two methyls, 1,2, can both be forward. These are tetrahedral carbons. 2 in the plane, 1 forward, 1 back, right? 2 in the plane. The blue is forward, towards you guys. The other black one is back, yeah? Okay. Both tetrahedral. So you can have this option. Both methyls could be forward, and when we make a bold bond like this, that means it's projected forward. You start out skinny, and as it goes, it's like if I'm looking at it and the methyl's coming forward, it gets bigger as it gets closer to it. So this is supposed to be getting bigger here. All right? Both coming forward. Over here, they're both going back. It's basically, I can hold my hand like this. All right, I got two fingers there. That would be both forward. Two groups right next to each other. Okay? But it would be both going the other way. This is called cis, which refers to, or basically means same side. Okay? Same projection. And these two are actually the same exact compound. Because this is just flipped over. It's like my hand. If my thumb is forward and I just do it like that, now the thumb is back. It actually doesn't work for the hand, but it works for those molecules. And most of this is covered during test 2. Right now we're looking at the idea of different isomers and cis. Okay? Test 1, I think, are more like test 2. Over here, these are opposite. You see that? And these are called, opposite called trans. Trans officially, I think, means across. Like transcontinental. The railroad went across the continent. They're across from each other. I typically would say opposite. One could be forward, the other back, but then you can also have one back, one forward. Are these the same? No. In this case, they're not the same. And we'll learn during test 2 how to understand that and judge that. Okay? And usually I'll show you this, and I'll say, remember when you looked at this? Okay, so how many different stereoisomers up here of 1,2-dimethyl cyclohexane? How many stereoisomers on the board? 3. 3, right? We have 1, 2, 3. Because these are the same. I mean, I could draw this 100 times. It's still only one compound, right? 1, 2, and 3. 3 different stereoisomers. What is a stereoisomer? Not a constitutional isomer, but a stereoisomer. Stereo refers to space. 3D, how groups are projected. All of these are connected at 1, 2. But the projection is different. Okay? Need to know what a stereoisomer is. It's basically the other type. If it ain't a constitutional isomer, well, it can be no isomer. But it's an isomer. First off, it's an isomer, which means it has the same formula, right? All of these structures have the same formula. They differ by stereo. They have this same connectivity. Don't confuse stereo with connectivity. Both of these have just look at these two. Stereoisomers. They both have the methyls connected at 1 and 2. Connected at 1 and 2. Everybody agree? So the connectivity is the same. The projection, the stereochemistry is not being considered there. All right? doesn't matter how they're connected, as long as they're connected at the same spots. Constitutional, you see up here, these do not have the same connectivity, because that's one, the methyls are at 1,2, connected at 1,2. Here they're connected at 1,3. So that is a different connectivity. Okay, so that's an introduction to that. And with the dye, this brings in some things here, some terminology and some ideas. So that's why we're going to look at dye substitute. Okay, let's look at, there's some drugs with lots of cycloalkane rings. Okay. Cyclopropane rings are actually very common in drugs. Even though it's ring strain, it can be made, and it's pretty prevalent. Down below, it talks a little bit about the ring strain. We expect 60 degrees. The bond angle is, though, actually not 60 degrees, because there's a difference between bond angle between carbon, 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 and orbital angles. The interorbital angle is actually 104 in cyclopropane. Okay? We'll look at that. Because the best, these are sigma bonds around this ring, and the best sigma bond would be like this. Okay? Head to head, right? That doesn't mean, here we go, head to head, straight head to head. That doesn't mean we can't make a bond that's maybe like this, not exactly head to head. The overlap is weaker, it's going to be a weaker bond, it's going to be thus a more high energy bond. You see, cyclopropane can't bond 1 to 9.5 more traditional. And can you see how these orbitals are not exactly head to head? They're more a little bit like this. Okay. Let's look at next page here. And this type of stuff. Let's go back to regular alkanes and look at rotations of regular alkanes. Then we'll go and look at the conformations of cycloalkanes. If we have a molecule, regular alkane, okay, like butane, 4 carbons, and these little guys would be H's, and pretend there's 3 H's here. 1, 2, 3, 4. Okay, just good old butane. Boom, boom, boom. Yeah. We're good with line bond structures. 4 carbons. What is this? C4, H. C4, H10. Two, 4 H's, 3 here makes 7, 3 more here make 10. Okay. Can this bond rotate between these 2 carbons? Yes, it's a sigma bond. Okay, rotate. Well, look at this. If this methyl is down, how is this other methyl going to exist? Will it be down with it? Will it be to the side? Will it be up, opposite? This is what we want to look at, is when alkanes can rotate, how are other groups going to exist as it rotates? And how do you draw this on your paper? Okay, let's get at that. Now this is just ethane, 2 carbons. And there's different ways to show it. We can just show a simple sort of semi-line bond. It's not full line bond, and we're showing carbons instead of just points. There's many ways to show compounds. If we show the full stereochemistry, the projections, we see the carbon is tetrahedral, 2 in the plane, 1 forward, 1 back. Right? So we can draw that. More of a 3-dimensional form or stereo view. Sawhorse structures are common, but not that common. Not for us. We're not going to see sawhorse. We may come back. After we talk more, we can sort of show or discuss what this is trying to show us. Ultimately, though, how do you draw this? Draw these. You can draw it like that. Another common way is to draw this type of thing. What is that? Newman projection. Newman was a chemist at Ohio State back in the 60s, 70s, 80s. And he developed this way of showing this, and it's very convenient. How do we do this? You look at the compound over here, okay? And what do we see? I'm over here. Let me add H's to this. There's going to be 2 carbons. Now we're going to have blacks as H's on each carbon. So we have them all just like that structure there. So 2 carbons and then 3 H's coming off. Let's see, this H is straight up. Over there we have the H straight down. Over here we have an H forward, bolded. We have an H back, dashed. Over there we have an H bolded, coming forward. It's also going a little up. And then we have one back, but it's also going a little up. Does that seem to be like this? Okay. I'm over here. What do I see? I'm looking at the front carbon, and then there's a carbon behind it. You want to see what I see? How about if I do this? I'm looking at it like that. Right? And how can I draw that? We draw that using a circle, circle, dot, dot. Remember that? Circle, circle, dot, dot? Nobody?
Now I got my cootie shot, that thing.
Thank you. We draw a circle, big circle there, and we put a dot in the middle. Okay? Circle and then the dot in the middle. And the dot in the middle is the front carbon. Okay? Again, I'm looking at this. I see the carbon. I see a carbon behind it. Actually hard to see the carbon behind it because it's in front of this one, or behind this one. But on the front carbon, what do I see? I see an H going straight up. Okay? Here we go. I'm going to turn so you can see what I see, because you can't come down here and stand on the chair. What am I seeing when I stand on the chair? Seeing this. Okay? How about if I hold it right here? Right? Draw that on the board like that. That's what we're doing. The front carbon is the dot. I see an H coming straight up. That's that one. I see an H going down and to the right. That's that one. I see an H coming this way and a little bit down. That's the front carbon. And that's what we got over there, right? Now the back carbon, if I'm looking here, I really can't see it. It's blocked by the front one. But I see an H coming out there. You see, I can't see behind this, so I can't see that bond. It's almost like there's a disc right here that's blocking parts of the back. What else do I see in the back? I see an H straight down, and I see an H like this. And these are supposed to be the same, and that's how they got to that. There. Okay, we'll do many examples of this. It's called a Newman projection. Different way to draw it. Same compound, we're just drawing it like this instead. It's going to really let us see bond angles. Now, we're losing some stereo view here. It has to be implied, because this is all flat on the board. This H looks like it's in the plane of the board, but it's actually coming forward a little bit. If I put a plane here, these 3 H's are actually coming towards you. But I don't show these bolded or anything. That has to be kind of implied. All right? So this has very accurate 3D. You're losing some 3D here, but you have to just know it's there. It's implied. Okay, now we can also show rotations, because if we start here, Now I can maybe rotate the front, and when I turn this, I'm really turning this bond. Okay, I'll just spin that. But the bond is rotating. If I rotate the bond, you see how the front spins? Okay. So instead, I'll just spin it. As we rotate the bond, this can come around, and now we can discuss and show things better than the other drawings. So this became very popular and moved into the organic textbooks and then moved into your life. Okay? All right, we can also see things like dihedral angles. Okay? What is the dihedral angle between this H and that H right there? All right, what is a dihedral angle? Di means two. We got two planes. Okay? What is the angle I drew here? 90 degrees. Okay? But that's just a monohedral, single plane on the board. A dihedral would be if, okay, I'm going to draw a line there, but the other line is not going to be in the plane. Okay? What if instead I have another plane and it's over here? What is the angle between that and this? It's still 90 degrees. It's just like this, except this has been moved to a different plane. I can take it back to the same plane, and now it's a monohedral angle. Now it's a dihedral, two planes. Okay? All right? But what if this went like this compared to the other? Just change the angle. Okay? Well, it'd be the same as this. Okay? What if it was like that? If that was a carbon or something?
180.
Linear 180. Well, what if this was out here? It's still 180. Okay? Same thing here. What's the angle here? Well, if this H was here, that would be a 90 degree. Because, see, that one is in the front and back. Well, in the front, let's get rid of this. Well, in the front is straight up, and the one in the back is there. Okay? I mean, I don't have to redraw it, it's already here. So this one's in the front, so this is this plane, and the other one's back here in this plane. Just see it there. What is that? Anybody have a suggestion? You can get out your, what is it called, a protractor? Is that what it's called?
Yeah.
Look at this. This and that is the same, and that is the same. They're all three. That is 180 because they're opposite. So a third of 180 is what? 60. Yeah, see, each of these is 60-degree dihedral angles. And 60 gives you 180, and then 60, 60, 60 more gives you a total of what? 360 would be rotating all the way around. Okay? So it allows you to see dihedral angles better, and there it's trying to illustrate what I just tried to illustrate. Okay, we can go back to butane, and for butane, I'm going to get rid of the H's and call now each thing carbon, and then the H's are just sort of there. All right, so just a carbon skeleton. These two little guys can serve as H's. Here, this is with the front methyl up and the back methyl down. You see that? That is on the back carbon, right? The initial dot is a front carbon. The back carbon is back behind there. We can't see it, but we can see the methyl back there coming down from that back carbon. Okay? So that's like this. And these methyls here are said to be anti. One is straight up over here, the other one is straight down. Kind of like trans, but we use anti here. And we'll distinguish when we use best. Okay? Here the two groups are, the front one is straight up, and the methyl is to the side. That's a 60-degree dihedral angle between the methyls. That's called gauche. I think that's French. You might know French. Good. Okay. I think it pretty much means to the side. Okay? The methyls are sort of side to each other. You can also see these space-filling models. Ultimately, anti is best. When this thing can spin around, it's best, and we asked this question when we started. How are these tubes going to exist to each other? And the answer is they would rather be kind of opposite to each other. Okay? And that's called anti. And if you look at the space-filling model, see, this is really H's here. There's some space here. And if you put these up, the space crowds each other. Okay? Imagine two volleyballs here, or softballs. They're just close to each other. So it'd be like, okay, I got more room here to breathe. Okay, anti. Too close. And if you look at these closely, you can see how the crowding is here when they're, what do we call it when they're both kind of up like that? That's anti. What can we call that? Cis is analogous to what we saw previously, but it's actually, here it's called syn. When you can rotate, we usually use syn and anti. Cis and trans is usually used when you can't rotate. We'll have plenty of time to distinguish. All right? But they are synonymous. Okay, when they're syn, that's not good. That's the worst. And the dihedral angle is what? Here we go. You can see the dihedral angle. Here we go. Right now, you guys, what's the dihedral angle between the two methyls? 90. Yes. Okay. How about now? 0. There's no angle. Okay. Now, this looks like there's a little bit of difference. This is drawn like that because maybe let's draw one from scratch. Draw one from scratch. Draw this on the board like that. Okay? And we also now have a butyl group. What if the two methyl groups were syn? What do you see on the front carbon? Front carbon. I see a methyl straight up. Okay, everybody knows what a methyl is, right? It's a CH3 group. Methane is CH4. When it's a substituent, you have to lose an H so it can bond to something else. We don't no longer call it a methyl. I mean a methane. We call it a methyl. The YL ending indicates it's now a substituent. What if a benzene was a substituent? It's actually called a phenyl. What'd you call it? Benzyl is actually a little bit more. So, like we talked about exceptions. Okay, so the YL ending. So that was in nomenclature, yeah? Now with a CH3, I typically do ME, all right? But I could have just done CH3. Very common to use ME. All right, what do we see here? We see H. And we see H. What do you see on the back carbon? What's going straight up on the back carbon? Methyl. We also have other terminology. Those are syn. We also sometimes say that they're eclipsed. Does that make sense? Like you can't see the sun because the moon is in front of it. You can't see the back carbon because the front one is in front of it. Right? You have to assume it's back there. So how do we draw it? I could just say, well, it's back there. You just can't see it. We don't do that. We draw it a little bit to the side, okay? And you don't want to write on top of each other. But see right here? This is eclipsed. And it's supposed to be exactly 0 degrees. But you still draw it there. Same thing here. What's behind this H? There's another H back there, and they're eclipsed. And we can draw that. The back one I drew a little bit to the clock right. So I'm going to draw the one back here a little bit to the clock right. And this one is also an H over here. I'm going to draw it a little bit to the clock as if the clock kept going around. There it is in a fully eclipsed. One thing we need to look at is energy here. Energy diagram. And let's finish up making some comments about this. I'll go back to ethane. Put H's back on here. And let's do a quick tour around the world here. We'll end there. The first one. Front H is straight up. The back H is straight up. The H's are eclipsed. All H's are eclipsed if you look at your model. Okay? That's the highest in energy. If we start rotating, which carbon are we rotating, front or back? Rotating the back carbon. If we rotate the back carbon, typically we rotate 60 degrees. Now we have this. That's lower in energy. And that's called staggered. Okay? All those are eclipsed. This is staggered. We have two main types, eclipsed or staggered. Staggered is things are gouged to the side. Okay? If we keep rotating the back, we come back to here. It's actually identical to this one, so the energy goes back up. And we can keep rotating around. I'll let you do this. Let me say this. When we rotate it from here, okay, start rotating. Low energy. I'm rotating. See, the energy is rising. Boom. We go to the absolute worst. Okay? But then it starts moving again. Oh, I'm getting better, 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 better, better. Boom. That's the best I can get. Because now I'm fully staggered. If I keep going, now I'm going back to now eclipsed again. Okay? This syllabus told you where you can get models if you want. I'm trying to just get you into this so you can be looking at this over the break. Give you enough. We'll try to pull things together on Wednesday. Yeah. This and then the last topic. Please also be doing the homework on the purple. Okay. And then the very last topic here, what I call big topic, we've got a lot to go back on, is dealing with cyclohexanes. Chair conformations. Okay, please be reading about that as well. Have a good weekend, guys. See some of you this afternoon.